So, we will continue our discussion on different canonical laminar flows. So, in last lecture we saw flow due to motion of a plate. So, we have two parallel plates which were set into motion differentially. So, what we did was we had the bottom plate held fixed and the top plate was set into motion. Then we looked into a problem which was a flow that was between two plates, but now driven by a pressure gradient. So, there was a pressure drop that you had, and based on that we obtained the velocity profile. So, I will do two variants of these problems because typically we look at these problems with the given boundary conditions that we have already solved. So, the first variant, so this is going to be the third problem we are going to look into, where we will revisit the plane Couette problem. So, you have a top plate that is moving. So, the x velocity is u bar at the top, the bottom is held fixed. It is the same problem in terms of the geometry. One key difference is that the plates are no longer impermeable, they are porous plates, which means that there is some velocity of fluid that is being injected through this system. So, you have a velocity v bar with which fluid is actually rushing in through the top plate. So, imagine the top and the bottom plates, instead of being impermeable plates, these are like filters. So, they have holes in them and you are pushing fluid at a certain velocity through these plates. So, the question is going back to what we did in our earlier lecture, deriving the velocity profile, how much of that would change because of this modification to the problem. So, if you remember, we looked into the steady state equation, which was the following. And then we did not have any body force, but we obviously have our viscous term. So, I am going to ignore the body force in the problem for the time being. And we are saying that the flow is fully developed. So, if I write this down in terms of component, I have a rho dou u dou x v dou u dou y is equal to minus dou p dou x plus mu dou square u dou x square. And for the y momentum equation, we have rho u dou v dou x v dou v dou y is equal to minus dou p dou y plus mu dou square u dou y square. Sorry, this is mu dou square v dou x square, because the additional term that you have here, which is dou square u dou, let me write the full Laplacian. So, the first term is going to be 0 because of fully developed assumption. So, these are 0 since we are assuming the problem to be fully developed. The same applies for the term u dou x, because dou u dou x is 0, dou v dou x is also 0. Now, if you recall from continuity, I had dou u dou x plus dou v dou y is equal to 0, which implies that because dou u dou x is 0, I have v is equal to a constant v naught. And if I apply the boundary condition that v should be equal to the fluid velocity at the boundaries, that means v naught is basically my v bar. So, the velocity in the y direction is a constant based on the fully developed assumption, and now because the boundaries, the walls are permeable, there is a certain fluid inflow and outflow through the top and the bottom wall. The vertical velocity or the y component of velocity is the same constant value throughout the domain. So, v is a constant. Now, because v is a constant, this term goes to 0, so would this particular term, and we are not applying any pressure drop along the x direction. So, we are back to an equation which is rho v dou u dou y is equal to mu dou square u dou y square, and v is a constant, so I can write this as v bar. So, you can write this now as v bar divided by nu, the kinematic viscosity, dou u dou y is equal to dou square u dou y square. Now, this is obviously only varying in the y direction, so I can write it as an ordinary derivative, and I can integrate this and solve this equation. So, I can now take this equation d square u dy square minus v bar by nu du dy is equal to 0. So, the solution, I can write this as d dy of du dy minus v bar by nu u is equal to 0. So, u is du dy minus v bar by nu u is equal to some constant c. So, if you now, let us call it C1. Now, if you solve this further, you will have u of y is going to be C2 e to the power plus v bar by nu y plus e to the power plus v bar nu y integral C1 e to the power minus v bar nu y prime dy prime 0 to y. So, you will have now a solution in this particular problem, which is u of y is C2 exponential of v bar by nu y and on integration you will have C1 minus nu by v bar exponential of minus v bar nu y minus 1 as your solution. So, you can now apply the boundary condition at u is equal to 0 at the bottom plate and u is equal to u bar at the top plate. So, you have a vertical velocity that is there in this problem. So, there is an inflow that is there in this particular problem. So, if you apply the boundary condition C1 and C2, you will be able to find what C1 and C2 should be such that you satisfy the two boundary condition. So, what I will do is I will directly sketch, instead of spending time working out these constants, I will directly sketch what the velocity profile should be. So, you know that at y equals to h, the horizontal velocity should be the plate velocity, and at the bottom plate you have a velocity which is going to 0. So, what you will have here is a velocity profile that would roughly be very close to being 0 away from the top plate and then approach the top plate velocity in the top region. So, think of what is going on here. So, there is this term v bar by nu. V bar by nu is giving you a sense of length scale. If you see the quantity v bar, which is a velocity, and this is nu, which is the kinematic velocity, this has units of a inverse length scale. The numerator is meter per second, the denominator is meter square per second. So, this particular object has a dimension of an inverse length. So, if this quantity was large, so if L was small, L basically being nu by v bar. So, if L was small, that means that the prefactor of du dy is going to be very large, right. This particular equation I could write down as 1 by L du dy is equal to d square u dy square. So if I have a very small value of L, then I will have this term du dy dominating over L d square u dy square. If I just do it in a without putting too much of a thought, I have a solution here. I mean, without getting stuck into the algebra of finding the constants, think of the differential equation. The differential equation is d square u dy square is equal to a inverse length times du dy. Now, if this length was actually small, this is a length kind of quantity, v nu by v bar. If this was small, then I can start thinking that the LHS is actually much more dominant over the RHS. So, my temptation is that when L is very small, I can approximate this equation as du dy is equal to 0. That is what I would think should actually happen. Now, which has a solution, which is obviously u is equal to a constant. Now, where is the problem? The problem is that when you have this particular solution u is equal to a constant, you can only satisfy the boundary condition on one of the surfaces. You can't satisfy on both the surfaces. You can either say that I will satisfy at u equals to 0 at the bottom plate or u is equal to a constant at the top plate. You won't be able to actually satisfy the boundary condition everywhere. So, this tells you that in this particular problem, when you have L being very small, this particular parameter L is nu by V bar. When you have this particular parameter, you will not be able to apply the solution uniformly, which is to say that this description du dy being equal to 0, this description is going to work near one of the boundaries but not both the boundaries. So, depending on whether L is positive or negative, whether V bar is going from top to bottom or bottom to top, you will have solution profiles which will look something like this, either like this or something which will look like this. So, you will have a thin region near each of those plates where the higher derivative or the viscous term. So, your equation was 1 by L du dy is equal to d square u dy square. This is the equation that you had. Now, we said that when L is small, I can ignore the right hand side. And now what I am trying to motivate you in thinking is you cannot do this uniformly. You cannot do this on both the plates. You can work, this is a simple ordinary differential equation. So, you can work out the solution and based on the sign of L, you will either have a solution which will approach the top plate velocity in a convex or a concave manner. So, it could either remain almost u bar over the entire region and then sharply dip to 0 in the bottom plate, or it would remain 0 throughout and then very close to the top plate it will transition to a uniform velocity. So, you see what's going on, right? So, if you have the velocity which is where the fluid is actually being injected from the bottom, if you have the fluid being injected from the bottom, there is barely going to be any horizontal velocity in the bottom region. But then when it approaches the top plate is going to shear and move a thin layer of fluid. Whereas now if you have the fluid being injected from the top, so which means that V bar in this case is negative. So, this is when L, which is defined as nu by V bar, is small but a negative number, then the fluid is basically going to get pushed down. So, whatever is the momentum that is there in the top, which is the fastest moving. So, the fluid layer which is close to the top plate will always be moving with a velocity u bar. Now, before you do the math, you think in terms of what is happening in terms of momentum transport. So the fluid layer close to the wall wants to move with the velocity of the wall. So the one which is at the top wall would want to move with a velocity u bar. The one which is at the bottom wall would want to be stationary. That is unambiguous. Now the question is, what should the velocity profile look like? To see what the velocity profile looks like, you have to now see that injecting fluid from the bottom and injecting fluid from the top, they are not the same. Because if you are injecting fluid from the top, then what would happen is you are actually pushing fast moving fluid which is near the top plate to the bulk. Whereas if you are injecting it from the bottom, the fluid near the bottom is anyway quiescent. So you are not really transporting any amount of x momentum. So this is a term which is basically saying that there is an advection of your x momentum by the vertical velocity. See, how did you get this term? This term came from v dou u dou y. So this term tells you there is a horizontal momentum that is basically being created by fluid parcels being carried from one region in x layer to another region in x layer by vertical transport. In the previous problems that we did, there was no vertical transport. It was a problem where it was unidirectional. The flow was only in the x direction. Now what we are saying that the flow has an x direction obviously, but it also has a y directional component. And we have chosen a very simple problem where the y directional velocity is constant. So there is a constant y velocity, but that is telling us something very interesting, that this transport in the y direction is taking a parcel here and taking its momentum and transferring it to a higher elevation. Now obviously in this particular problem, the fluid that is at the bottom level when there is a transport happening vertically going up is reasonably stationary. So the x momentum is very low. So you don't have a lot going on here. So the x velocity profile is almost as 0. But the moment you get close to the plate, there is a viscous diffusion which is going to be important. So you will have viscous diffusion playing a prominent role close to the top plate, where no longer this term can dominate. You will also need to account for viscous diffusion there. And so you will have this thin layer where the velocity will transition from being nearly quiescent to u bar. Now if you see that scenario here, if you consider two levels, so there is a fast moving fluid that is there near the top plate. Because the top plate is generating the motion, there is a fast moving fluid. Now the vertical velocity is actually aiding it. It is acting in favor of transporting the fast moving fluid. So it is continuously making the bottom layers move equally fast, if not as fast as possible. So there is this continuous transport till it comes close to the bottom plate, where viscous diffusion is going to compete with advection. So this is a competition of advection and viscous diffusion in your momentum transport. So you can get the complete solution by solving this linear ODE, but before you do a complete solution, it is important to understand the significance of the two terms. There is an advection term and there is a viscous diffusion term. This is a viscous diffusion of your horizontal momentum or the momentum in the x direction. This is a transport of your x momentum by a vertical velocity or y velocity. So when we write the term u dot del u, that term actually signifies that you can have an acceleration or transport of momentum along the direction of motion, but you can also have a transport of momentum where faster moving fluid. So if you have a flow where there is a variation in velocity, it can take faster moving fluid from one region and transport it to another region and thus change the momentum. Or in this case, for instance, it is actually inhibiting the transport because it is trying to push the fluid further up. It doesn't want, the transport is against the direction in which viscous diffusion is going to act. So the one primary reason why this is something which I am doing right now in a part of laminar flow, that you can start now thinking that should this fact that there is a certain region over which viscous diffusion and advection compete, appeared naturally. So if you see there is this L, and I am saying that when L is very small, I should be able to drop this, and we arrived at a contradiction where dropping it doesn't give us the solution uniformly valid over the entire region. If you do L being positive and very small, then you are going to get this scenario where the solution from advection is uniformly valid, or rather is only applicable over a region that is from the bottom plate to a region very close to the top plate. Similarly, when L is negative and very small, you get a solution from du dy being equal to 0, giving you nearly uniform profile that is applicable from the top plate to a certain region very close to the bottom plate. Now, how close are you actually saying that this is applicable, or where this breaks down? So, if you now see this, I can define a coordinate which is y divided by L. I will design a new coordinate system which is y divided by L. So, in this new coordinate system, d dy is going to be 1 by L d d eta. So, on the left hand side, I will get 1 by L into 1 by L d d eta of u, and on the right hand side, I am basically going to get 1 by L square d square u d eta square. So, what do you get? You get du d eta is equal to d square u d eta square. Now, there is no L in the problem. So, in a coordinate, vertical coordinate that is actually stretched by that length L, you see what is eta here? Eta is y by L. So, if you say L is very small, then when y becomes very small, y by L will become an order 1 number. Right? This is basically kind of magnifying the region. So, in this new coordinate which is y by L, if you write in terms of the variable that we have in the problem, this is y times v bar by nu. So, there is a length scale over which advection and diffusion can be shown to be equally important. And this is basically your introduction to a topic that will come in some time, which is on boundary layer. That you are already seeing through this very simple problem that advection and diffusion can necessarily not just be seen as separate. There are regions in the problem where even though you might, so if you think of L being very small, it means that du dy is equal to L d square u dy square. So, here just because L is small, that length scale is small, doesn't mean that I can drop my viscous term. Viscous terms need to be kept, and viscous terms have to be kept especially in a region very close to the wall where viscous diffusion will be as dominant as advection. So, if you think of L in some ways, if you were to non-dimensionalize your y and u, L will basically give you, if you non-dimensionalize your L with, let us say, the height of the problem. So, if you take L by h, then this is going to be nu v bar h, and that is the Reynolds number. So, you are already seeing this feature come up. So, we will do this obviously in a lot more detail when we do boundary layer, but this is already an introduction for you to see that in fluid mechanics problems, when you have a small term multiplying your viscous effects, it doesn't necessarily mean that I can drop viscous effects uniformly everywhere. So, just through this classical problem of flow between two plates, the only modification that we did is we said that there is a vertical velocity. So, because there is a vertical velocity, the problem becomes modified because now it is no longer that viscous force is equal to 0. There is a balance between viscous force and the acceleration that is there in the problem. Now, the acceleration here is not responsible for the velocity changing in x, but there is a vertical transport that is there. So instead of thinking of it as an acceleration, you can rather think of it as a momentum transport. That I have different layers of fluid, each moving with different velocities. So when you think of a shear flow, you are thinking, if you go back to this picture of slabs, fluids basically broken into slabs, and you say that each of these slabs are moving with different velocities. If you have this kind of a cartoon. Now, how do the slabs actually communicate with each other? The slabs are communicating with each other through viscous diffusion. This is the part which we discussed in the last lecture. That think of these like stacks of books, each have friction between them. As you try to slide one book over the other, it is going to create motion in the other book. And depending on whatever the driving mechanisms are, you are going to get some equilibrium profile. So you get a plane co-ed flow, you get a plane channel flow, etc. You can do all of these things. So that is just about the effect of momentum transport due to viscous diffusion. But you can also have a momentum transport which is happening because of velocities which might exist in the other component. So if there is a vertical velocity here, then fluid parcels which are moving with velocity, let's say u4, that is being transmitted to a layer above where the fluid is moving with u2. So what is going to happen? If I take a faster moving fluid or a slower moving fluid and bring it to a neighborhood where the fluid velocity is different, I am going to alter the momentum. So that is another way of thinking of momentum transport. So finally the entire picture is all about momentum transport. There is momentum transport due to viscous diffusion, there is momentum transport due to advection. And this is a problem where both are actually competing. And what we saw is that competition in this case, even if you say that there is a parameter multiplying viscous diffusion which is very small, doesn't mean that that competition is always has advection winning everywhere. Advection wins over a large part of the region. So we said that the term multiplying viscous diffusion is a very small term. That doesn't mean viscous diffusion is insignificant. Viscous diffusion is almost negligible for a large part of the domain, but near one of the boundaries, it picks up. It picks up and becomes as important and comparable as advection. So this is for you to start already thinking about what you are going to expect in boundary layer, where the details are going to be much more than what we did here, but this is the basic idea of boundary layer, that advection and viscous diffusion both become equally important near surfaces. You cannot ignore viscous diffusion uniformly over the entire region. So whenever you have flow past surfaces, momentum diffusion due to viscosity for whatever small value of this parameter, which is inverse of Reynolds in this problem, cannot be neglected. Okay, this is an interesting problem to actually see this in action. We will do one more modification to our plane channel problems. So the modification we will do is the following, and this is again a setting that you might have seen in scenarios where you have a layer of water that is trickling down a surface. So when it rains and the road is gently sloped, you have water basically running over that surface. So this is a solid surface, this is air, and this is water. This particular layer is water. Now this is a problem that is driven by gravity. Gravity is driving the motion. So we want to find what is the velocity profile for this particular scenario. So we go back to, and there is an inclination, which is why you have this particular motion being driven. So we go back to writing our equations. So I have rho u dou u dou x plus v dou u dou y is equal to minus dou p dou x plus mu dou square u dou x square. I am again doing everything in 2D, dou y square, and then there is a body force. Now this is where I need to mention, because I have not clarified what is my x and what is my y direction. So I can obviously continue choosing x as my horizontal and y along gravity. But here, because the surface gives me a natural choice of coordinate system. So what I will do is I am going to assume that this surface is my x-axis instead of what I was doing earlier, and the direction normal to the surface as y-axis, because that is a natural boundary condition. The interface and the bottom wall are surfaces of constant y. So this is y equals 0, this is y equals h. So now in this particular coordinate system, there is a body force in x direction, because g, if you were to resolve, there is a g sin theta which is along the x direction and g cosine theta which is pointing in the negative y direction. The acceleration due to gravity would have these two parts. So in the x direction, I will have rho g sin theta, and now if I write my y momentum equation, that will be u dou v dou x v dou v dou y minus dou p dou y plus mu dou square v dou x square dou square v dou y square plus, now here the body force is acting in negative y direction, so instead of plus this should be minus rho g cosine theta. Now what are the assumptions that we are making? Besides, we have already made the assumption of steady state, but now what are the assumptions that we make? We make the assumption it is fully developed. So when we say it's fully developed, that means that the motion along x for the velocity components are 0. Now that automatically from continuity implies that v is equal to a constant. Now if v is equal to a constant, that y equals 0 is an impermeable surface. So the boundary condition is that y equals 0, you have v is equal to 0. It's a no slip impermeable surface, so u and v both should be 0 at the bottom surface. So if v is equal to 0 and v is a constant elsewhere, then the only constant that is possible is v is equal to 0 everywhere. So there is no vertical velocity, there is no y component of velocity in this particular problem. So now that makes our life significantly simpler, and there is flow is fully developed. So I arrive at the set of equations. Now I am not applying here, so let me just, so I have 0 minus dou p dou x plus mu dou square u dou y square plus rho g sin theta 0 minus dou p dou y minus rho g cosine theta. So if I integrate this, so this is my fully developed steady state equations. If I now integrate this, I will have dou p dou y is equal to minus rho g cosine theta. On integration, I get p is equal to some function of x minus rho g y cosine theta. So here the reason for choosing this problem will get clear to you. So the bottom surface is nothing unusual, but the top surface is actually a surface between air and water. So this is an interface between two liquids. So we have learned that when you have an interface between two liquids, we need to apply our boundary conditions there. Now, what are the boundary conditions that we have? We have kinematic boundary condition, we have dynamic boundary condition. Now, the kinematic boundary condition tells us that if there is an evolution of the interface, then that is going to be related to the velocity, vertical velocity at the interface. Now, the interface here we are assuming to be flat. We are not thinking of any waves on the interface. So, we consider the interface to be completely flat in this particular case. The dynamic boundary condition has two parts. The first part is regarding normal stress and the second part is regarding tangential stress. Now, the normal stress boundary condition tells us that there can be a jump in normal stress if you have surface tension. So, if I am saying that the interface remains flat. So, if you remember, the boundary condition was n dot sigma dot n over the interface was kappa divergence of n. Kappa is the surface tension. I think I took, did I take kappa? I took gamma, I think, yeah. So, gamma was the surface tension, divergence of n. So, divergence of gamma is surface tension. Now, the interface is a flat interface, which means divergence of n should be 0. So, then I have no jump in normal stress. Now, normal stress has two components. One is pressure and the other is the viscous normal stress. Now, viscous normal stress will have terms like dou u, dou x, dou v, dou y. All of these are 0. All the viscous normal stresses would be 0 because u doesn't vary along x by fully developed assumption and v is precisely 0 everywhere. So, the normal stress is only a jump of pressure. So, it tells us finally what you arrive at is that pressure at the interface is going to be the pressure in air, which if we assume it to be unperturbed to be just atmospheric pressure. So, I am not going to solve for the flow in air. I will say that air is more or less passive. It is just applying a pressure boundary condition on the interface. There is no motion that is happening in air, and this is a reasonably good assumption that we are going to make based on the fact that the viscosity ratio is actually very high between water and air. So, if you remember that when we are going to now look into tangential boundary condition, the tangential stress boundary condition would be a continuity of tangential stress. So, in this case, the tangential stress is only sigma xy, it is a 2D problem. So, sigma xy should not be discontinuous at the interface. So, if you say the interface is y equal to h evaluated from the water and air, this quantity should not be discontinuous if there are no surface tension gradients, because this term is actually proportional to surface tension gradient. So, we will ignore all those details and we will say that the shear stress is actually continuous. But then you know that the shear stress is in this case related to mu dou u dou y. But mu between air and water is a ratio of 100. So, we are going to treat the air as passive and the boundary condition that we will apply is mu du dy is equal to 0 at the interface. So, this is known as a modification of this interface boundary condition to a stress-free boundary. So, when you have an air-water problem, you can make a reasonably good assumption by treating the interface as a stress-free interface, that the shear stress is equal to 0. This is basically based on the idea that you have such big disparity between the values of viscosity. So, now we have more or less everything. So, we have at the bottom plate velocity is 0, at the top plate velocity gradient is 0. Velocity is not 0 any longer at the interface, velocity gradient is what is 0 and pressure is equal to atmospheric. So, now which means that if pressure is equal to atmospheric pressure at every location, f of x has to be a constant, it cannot be a function of x, which means pressure at the interface is P atmospheric, which is now a constant minus rho g h cosine theta, which gives me that the value of pressure is P atmospheric plus rho g cosine theta h minus y. So, there is a pressure that you have from the hydrostatic balance in this problem, and that pressure is not going to drive any flow because the interface is exactly flat. So, the flow now is only driven by gravity. So, I can drop this from the problem and I have mu d square u dy square plus rho g sin theta is equal to 0, which is d square u dy square is equal to minus g by nu sin theta. So, now the process is, you are aware of the process. We will integrate this g by nu sin theta y square by 2. Apply the boundary conditions. The boundary condition is u at y equals 0 is equal to 0, which means a is equal to 0. So, u is equal to by minus g sin theta y square by 2. But the other boundary condition is at y equals h, it is not u, but rather du dy which is 0. It is actually mu du dy which is equal to 0, which translates to the fact that the velocity profile should have a maxima at the interface. So, if you integrate this now, du dy, you will get b minus g sin theta y evaluated at the interface. This is b minus g sin theta h is equal to 0. So, that gives me the constant b, which is g sin theta h. So, finally, I have a velocity profile now, which is g sin theta y h minus y by 2. There is a nu that I have missed somewhere. Yeah. So, this is a nu here. So, this is the velocity profile which goes to 0 at y equals 0, and it has a 0 slope or 0 shear stress at y equals to h. The velocity at the interface is no longer 0. This is g sin theta by nu h into h by 2. So, this is g sin theta h square by 2 nu. You can compute the flux. So, g sin theta by nu y h minus y by 2. So, you can find the volume flux per unit depth. This would be 0 to h u dy. So, 0 to h g sin theta by nu y times h minus y square by 2 dy. So, that is g sin theta by nu y square h by 2 y cube by 6 h 0. So, g sin theta by nu h cube by 2 h cube by 6. So, that is your times h cube. So, that the flux per unit depth would be g sin theta h cube by 3 nu. So, as you keep increasing the thickness of the film, the flow rate increases with the third power. Or you can think of it the other way around, that if you were to increase the flow rate, then the thickness of the film is going to go as q to the power 1/3. So, this is a problem which is extensively studied, which is a falling film down an incline. It's of both of interest in engineering problems when you are trying to coat surfaces. So, you have a surface and you are trying to coat a surface. So, this is a thin layer that is spreading over a surface which has an interface with air on top and a solid substrate. So, it's a coating problem. It's also an engineering problem, as I said, also a natural problem where you have a liquid layer which is spreading or falling over a sloping gentle slope. So, when you have rainwater that is going over a street, then there is this thin layer of rainwater which is going down a gently sloped street, and this velocity profile that you obtain here is a half parabola. So, the flow here is known as also a Nusselt flow. So, this was an example where we chose a boundary condition which is a little different than what we traditionally do for various internal flows. So, we used a boundary condition that is an interface boundary condition rather than a solid boundary condition. So, that is what we wanted to discuss regarding steady laminar flows. Now, you can also do problems in cylindrical geometries. You apply the same principles for problems in cylindrical geometries and you will obtain steady state velocity profiles. In cylindrical geometries, obviously, you have to be a little careful in terms of the fact that the equations will take a different form than the Cartesian counterpart. But the underlying approach of solving them in cylindrical geometries, whether you do a problem of flow through a pipe or you do a problem of flow between two rotating cylinders, they remain primarily the same. So, having done all these steady problems, we will next try to actually look into what happens when we relax these assumptions of steady state. Okay.